Hi everyone, my name is Noor-e, and this is my lab for oscillations. The purpose of this lab is to investigate the oscillatory motion of a spring mass system and apply the principle of conservation of energy. We recorded the motion using video analysis in Tracker and constructed a computational model to analyze the motion. We then calculated the energy changes over time and compared the computational results with experimental data to demonstrate energy conservation. Here are the key principles and equations used in this lab. The first is Newton's second law, which states that the net force equals the rate of change in momentum. Here, the net force is composed of two forces, the spring force and the gravitational force. The second principle that we will be using in this model, in this lab, is the energy principle, which states that the change in total energy is equal to the work done by the external forces plus the heat transfer. Here in our isolated system, energy should remain constant. On the right, I have other important equations that we will be using in our lab, such as the kinematic equations for velocity and position, the kinetic energy, which is 1 half mv squared, the gravitational potential energy, which is mgh, and the spring potential energy, which is 1 half kx squared. For this lab, I analyzed the provided video using Tracker software. On the left, you can see a frame from the video showing the spring mass system with the calibration stick and the tracking axes. The mass is tracked frame by frame as it oscillates in 2 dimensions. On the right are the X and Y position graphs generated by Tracker showing the sinusoidal oscillation patterns. Below that, you can see the data table containing the time, X position, and Y position values for each frame. So my procedure was, I used the calibration stick to set the scale. I then extracted the position data, which was then imported into my computation model and used as a CSV file. Here is the initial setup for my computational model. Here I set, from the video, I set the mass as 0.402 kilograms. I set spring constant as 6.8 newtons per meter, and I set the relaxed spring length as 0.123 meters. These are all from the video that was provided to me. So this is the code that we use to calculate the spring vector L, the unit vector L hat, and the stretch distance S. We then compute the initial energy's kinetic energy using 1 half mv squared and the gravitational potential energy using mgy. The spring potential energy is also calculated using 1 half kx squared, and total energy is just the sum of all of these g. Here we have the key calculations inside our while loop that run the simulation. First, we stored the initial energies. Then we calculate the gravitational force as a vector pointing downward and the spring force using Hooke's law. We sum these up to get the net force. Then apply Newton's second law to update the velocity and position of the mass. Next, we update the spring's length and stretch. Finally, we calculate all the energy changes, delta K for kinetic energy, delta U grav for gravitational potential energy, delta U spring for spring potential energy, and delta E for the total energy of all the system. These calculations repeat every time step to model the motion over time. Here are the graphs comparing our computational model in blue to the experimental tracker data in red. In the X position graph on the left, both curves show sinusoidal oscillations with a period of about 1.9 seconds oscillating between negative 0.11 and 0.11 meters. The model and data align closely. In the Y position graph on the right, we see the vertical oscillation between 0.78 and 0.63 meters. Again, the model tracks the experimental data well, though a slight phase difference develops over time. Our model, however, does not accurately perfectly reflect the experimental motion due to other factors like air resistance, which we didn't account for, and potential numerical errors from our time step. For our model system, the energy principle is satisfied. The orange curve representing change in total energy oscillates very close to zero throughout the simulation. This confirms energy conservation in our system. The kinetic, gravitational, and spring potential energies continuously transform into each other, demonstrating the characteristic energy exchange of the oscillating spring mass system and verifying that our model correctly applies the energy principle. From the tracker data, I estimated the oscillation periods in both directions. The x direction period is equals 1.71 seconds, while the y direction period is equals 1.614 seconds. Using the theoretical formula t equals 2 pi times the square root of m over k, we calculate a theoretical period of over 1.524 seconds. Both experimental periods are close to the theoretical value, with the the period of x being 12% longer than the period of y, and period of y being 6% longer. The x direction shows a slightly longer period than the y direction, which makes sense because the horizontal motion involves a larger amplitude swings. The small differences from the theoretical value are likely due to the coupled 2D motion and measurement uncertainties. Thank you.